Hi everybody! This video is a review video for Introduction to Space Science. We'll be talking about 5 different math problems that you might face on test number 2. So we'll go over those. Please pause the video as we're working on this so that you can see what we're doing and work it through yourself and think about why you're doing these steps. So let's get started. All right, let's take a look at our first question. We've got this atom here with a nucleus and an energy state, another energy state, and another energy state. Those energy states are labeled 0 eV, 5 eV, and 8 eV. eV is electron volt, it's just a unit of energy. So the ground state is the innermost state, which is also called the n equals 1 state. The first excited state is the next one, or the n equals 2, and the second excited state is the next one, or n equals 3. What are 2 ways to excite a ground state electron, when in n equals 1, to n equals 3? And what photon energies are necessary for each case? There's 2 ways to get a photon from 0 eV, the ground state, to n equals 3, 8 eV. 2 ways of doing that. Think about what the 2 ways are. Okay, so one way to get from 0 eV to 8 eV is direct. You start there, and if you get a photon with an energy of 8 eV, then that electron will go directly up to the 8 eV energy level, the n equals 3 level. But the other way of getting there is to start, of course we have to start at the ground state. We start at the ground state, and we get a photon that bumps us up to the n equals 2 state. And then from the n equals 2, we get bumped up again to the n equals 3 state. So to go from n equals 1 to n equals 2, we would need to get a photon of 8 eV energy. And to go from n equals 2 to n equals 3, we'd need to get a photon of 3 eV. So the first case, the direct case, 8 electron volts, direct. Second case, the indirect way, making a stopover at n equals 2, 5 eV, and 3 eV. So these would be your absorption lines in a real situation. If you sent in all the different energies of photons into a gas made of this kind of element, then you'd get some absorption of 8 eV photons, you get absorption of 5 eV, and you get absorption of 3 eV photons. All of these would be somewhat absorbed as the light goes through this kind of gas, because they would be being absorbed, those photons would be absorbed by electrons getting jumped up to higher energy states. Those electrons could later jump back down to n equals 2 or n equals 1, depending on where they were, and then emit those photons again. Next question. Let's look at orbits. The period of Mercury's orbit around the Sun is 0.25 years. It's actually 0.24, but I'm just going to say 0.25. What is the semi-major axis of Mercury's orbit around the Sun? Think about what equation you would use to solve this. I hope you're all thinking about Kepler's third law, which is this: p squared is equal to a cubed. Now, what in here is what? Which thing is p and which thing is a? P is the period. That makes sense. A is the semi-major axis. I guess it's the A for axis that can clue you in for that. Okay, well, what units does this have to be in? Well, if the period is in years, the semi-major axis will be in astronomical units, AU. That's how this equation works. It's actually very convenient. So we can just plug in 0.25 years. 0.25 squared is equal to a cubed. What's 0.25 squared? Well, that's 0.0625 is equal to a cubed. Now, a lot of people are going to struggle a little bit getting from this step to the next step. So think about what you do to get to the next step here. Okay. If you've got something that you need to solve for that's being raised to a power, so a cubed, you need to take the cube root of both sides. You need to raise both sides to the 1/3 power. A cubed to the 1/3 is just a. But 0.0625 to the 1/3, well, that's what we actually have to calculate. The answer ends up being 0.397, and as I said, the units are astronomical units. But how do you do this part? How do you get to the 1/3? And I know it's been a long time for many of you, so let me remind you. In your calculator, you can take your number, and you can use this caret button there. So 0.0625 caret, and if I want to do to the 1/3, I would do parentheses 1 divided by 3. If you don't do the parentheses, it's going to raise it to the first power and then just divide the whole thing by 3. So you have to put parentheses around it, and you hit enter, and you get 0.397, or close enough, if you can see that right there. Alternatively, you can raise it to the 0.333. That's the same thing. 0.333. 333. You get the idea. Hit enter, you get the same thing on there. Just like that, if my light doesn't interfere with it. There you go. Ah, you can probably see that pretty well right there. So that's how you do that. There's another way of doing this. Well, which is really just working in reverse and checking what we've already done. So let's assume that we did not originally know the period of Mercury's orbit, and we wanted to figure that out. But we did know that the semi-major axis was 0.397 AU. Let's remember our equation, p squared is equal to a cubed. So p squared is equal to 0.397 cubed. P squared is equal to 0.0625. That number should look familiar from over here. But 0.397 cubed is 0.0625. And then you can say, let's take, we take the square root of both sides. So the square root of p squared is just p. Square root of 0.0625 is 0.0625 to the 1/2, or we just write it as square root. And then that is a little bit easier. Most of you know your calculator. Well, mine, I go second, and then I go the times symbol to get a square root symbol, and then 0.0625, and hit enter, and I get 0.25, which is what we said in the beginning. We've done a couple things with temperature so far this semester. We'll do more, don't worry. So here's a question for you. What's the max wavelength of a star at a temperature of 10,000 Kelvin? So if you had a star that was at a temperature of 10,000 Kelvin, what would be the brightest wavelength, the max wavelength, that it would be emitting? Take a moment to think about what equation you would use to solve this. I hope you said Wien's law, W-E-I-N-S law, or Wien's law. Lambda max, lambda is for wavelength, maximum wavelength, is equal to B over T. Well, T is temperature. What's B? B is a constant, which I will give you on the test. All these constants I'll give you, and all the equations as well. You just need to know what to plug in where. So B is equal to 2.898 times 10 to the minus 3 meters kelvins. Meters times kelvins. All right, well, that actually simplifies things greatly because we can just plug in B and we can plug in T right there. B is 2.898 times 10 to the minus 3. T is 10,000 Kelvin. And we just plug that into our calculator. That's an easy one. And we find that the maximum wavelength is 2.898 times 10 to the minus 7 meters. That's also actually the equivalent of 289.8 nanometers. So this puts it in the near ultraviolet. This is just one way that I could give you a problem like this. I could have asked you, I could have given you lambda max and asked for T if I gave you B. Or, actually, I could have said, well, here's lambda max and here's T. Tell me what B is. That's another possibility that I could give you. That's actually how we discovered B originally, how scientists originally discovered what B is equal to. They had an object at a certain temperature, and they looked to see what the maximum wavelength was coming off of that hot glowing thing. Like, oh, well, B is this. And they tried it for a bunch of different temperatures, and they found a bunch of different wavelengths, and they saw that that number never changed. And it's like, oh, well, that must be a constant, because it doesn't change. And so that's how we came up with what B is equal to. Let's do another example with temperature. A star with a radius of 1 billion meters has a luminosity, or power, of 2.782 times 10 to the 25 watts. That's how much energy it's emitting per second. What is its surface temperature? Think for a moment about which law you would use to solve this problem. If you said the Stefan-Boltzmann law, right there, then you're right. Good. And we have most of the information that we need already. We've got power right there. This, E, emissivity, that's going to be 1. That's just always 1 for any purposes that we're going to do. Sigma, 5.67 times 10 to the minus 8, another number that I'll give you. And then T, we're looking for T. We need to figure out A. So what's A? Well, right here. The area of a sphere is 4 pi r squared, an equation that you have on the formula sheet. So 4 times pi times the radius squared, 10 to the 9 squared. That gives you your total area. So we find our area, 1.256 times 10 to the 19 meters squared. So we can plug that in. We've got our luminosity, our power, right there. We plug in there. We've got our area right there. We've got E is 1, emissivity is 1, sigma, 5.67 times 10 to the minus 8 times 2 to the 4th. Well, you ask your calculator what this is. So my calculator told me that it's this, 7.1215 times 10 to the 11. Then you divide both sides by that number. The left side of the equation, 3.906 times 10 to the 13, is equal to t to the 4th. We use a very similar procedure as to what we did previously for the other problem. And we raise both sides to the what power? Think about that. What do we do to both sides to make it t is equal to? All right. So we can raise both sides to the 1/4 power or to the 0.25 power. Those are exactly identical. Raising it to the 1/4 or raising it to the 0.25, exactly identical. T to the 4th to the 1/4 is just t. So T is equal to 2500 Kelvin. All right, last question. How fast is the Earth in its orbit around the Sun? What's the speed of Earth as it goes around the Sun? There's multiple ways of answering this. If you knew how long a year was and the distance around the Sun, you could figure it out. But what if the numbers that I gave you were the mass of the sun, the radius of Earth's orbit, and what g is equal to? It's Newton's gravitational constant. What method would you use to solve this, given this information? Think about that for a moment. All right, I hope everyone is thinking of this equation. The velocity of an object in a circular orbit is the square root of g times m over r. Well, velocity, that's what we're looking for. G, we're given that. M, that's the mass of the thing that is being orbited. That's the sun is being orbited. R is the radius of Earth's orbit. It's technically the distance from the center of the Earth to the center of the sun in this case. I will either tell you that it's the distance, that any distance that I give you would be the distance from the center of one object to the center of another object, or I would give you the height above, say it was the surface of the Earth, say a satellite was orbiting Earth at a distance of 300 kilometers above the surface of the Earth. Well, this r, the radius of the orbit, would be the radius of Earth plus the altitude of the satellite. In this case, the sun is pretty far away from Earth, so we don't have to worry about that. So in this kind of case, I just give you the radius of Earth's orbit, the distance from the center of Earth to the center of the sun, and you can plug that in directly, fortunately. So we do that here. V is equal to gm over r, and we find that the speed of Earth is 29,740 meters per second. That's really fast, of course, and that's almost 30 kilometers per second. Given that it's about 100 kilometers from here to Orlando, that indicates that it would take about 3 seconds to travel that distance at that speed, being approximate. So these things do travel very quickly. Now, sir, for a little bit of advice for you, as you're studying this stuff, first of all, you'll have your calculator on the test, and you'll have all these random numbers that you need. I'll make sure that you have access to all the numbers that you need to solve this kind of thing. What you need to do is, first of all, know which equation to use in which situation. There's many situations. We've just looked at 5 different situations here, each with their own equation they needed. So keep that in mind. Know when to use which equation and why. Second, know what all the parts of the equation mean. Each of these equations is different, and each of them is going to have different variables. You need to know what the purpose of each variable is, what it means, what units it would require, what kinds of things can be plugged into each part of the equation. Then you need to have, first of all, the confidence that you can plug these things in right, but also, in this kind of case, you're just solving for this side of the equation. Well, what if I gave you the velocity and the radius and g and asked you to find the mass? Could you do that? When you're studying, try doing an example problem where you're actually having to solve for this, and you know everything else. Or you have to solve for this, but you know everything else. Or you have to solve for this, but you know everything else. You can take these example problems, take the answer at the end, and once you have the answer at the end, you have all the numbers that go into the example problem. We'll just do the example problem again with knowing that number from the beginning, but forgetting this number, and see if you can solve for that number. That's a very good way of studying not just for this class, but any class that has a lot of math like this.